Discovering giant ore deposits with general systems and complexity is an epic tome. To alleviate some of the weight of this tome, the author will narrate the abstract and the conclusions. The introduced mineral deposit model is the product of a transdisciplinary study based on complexity and general systems theory. Both investigate the abstract organization of phenomena independent of their substance, type, or spatial or temporal scale of existence. The focus of the research has been on giant hydrothermal mineral deposits. They constitute less than 0.001% of the total number of deposits, yet contain 70 to 85% of the world's metal resources. Giants are the definitive exploration targets. They are more profitable to exploit and less susceptible to fluctuations of the market. Consensus has it that the same processes that generate small deposits also form giants, but those processes are simply longer, faster, and larger. Heat is the dominant factor in the genesis of a giant mineral deposit. A paleothermal map shows where the vast heat required to generate a giant has been concentrated in a large space and even allows us to deduce the durations of the process. To generate a paleothermal map acceptable to the scientific community requires reproducibility. Experimentation with various approaches to pattern recognition of geochemical data showed that the autoclust algorithm not only gave reproducibility, but also gave the most consistent, most meaningful results. It automatically extracts boundaries based on Voronoi and Delaunay tessellations. The user does not specify parameters. However, the modeler does have tools to explore the data. This approach is near ideal in that it removes much of the human-generated bias. This algorithm reveals the radial spatial distribution of gold deposits in the Lachlan Fold Belt of southeastern Australia at two distinct scales, repeating patterns every 80 kilometers and 230 kilometers. Both scales of patterning are reflected in the geology. The 80-kilometer patterns are nested within the 230-kilometer patterns, revealing a self-similar geometrical relationship. It is proposed that these patterns originated from Rayleigh-BÉNARD convection in the mantle. At the Rayleigh number appropriate for the mantle, the stable planform is the spoke pattern, where hot mantle material is moving upward near the center of the pattern and outward along the radial arms. Discontinuities in the mantle, Rayleigh-BÉNARD convection in the mantle, and the spatial distribution of giant mineral deposits are correlative. The discontinuities in the earth are acting as platforms from which Rayleigh-BÉNARD convection can originate. Shallow discontinuities give rise to plumets, which manifest at the crust as repeating patterns ranging from approximately 100 to approximately 1,000 kilometers in diameter. Deeper discontinuities give rise to plumes, which become apparent at the crust as repeating patterns ranging from greater than 1,000 to approximately 4,000 kilometers in diameter. The deepest discontinuities give rise to the superplumes, which become detectable at the crust as repeating patterns ranging from greater than 4,000 to greater than 10,000 kilometers in diameter. Rayleigh-BÉNARD convection concentrates the reservoirs of heat in the mantle into specific locations in the crust, thereby providing the vast heat requirements for the process to generate giant hydrothermal mineral deposits. The radial spatial distribution patterns observed for gold deposits are also present for base metal deposits. At the supergiant Broken Hill deposit in far western New South Wales, Australia, the higher temperature Broken Hill type deposits occur in a radial pattern, while the lower temperature deposits occur in concentric patterns. The supergiant Broken Hill deposit occurs at the very center of the pattern. If the supergiant Broken Hill deposit was buried beneath alluvium, water, or younger rocks, it would now be possible to predict its location with an accuracy measured in tens of square kilometers. This predictive accuracy is desired by every exploration manager of every exploration company. The giant deposits at Broken Hill, Olympic Dam, and Mount Isa all occur on the edge of an annulus. There are at least two ways of creating an annulus on the Earth's surface. One is through Rayleigh-BÉNARD convection, and the other is through meteor impact. It is likely that only large meteors, those greater than 10 kilometers in diameter, would have any permanent impact on the mantle. Lesser meteors would leave only a superficial scar that would be eroded away. The permanent scars in the mantle act as accidental templates, consisting of concentric and possibly radial fractures that impose those structures on any rocks that were subsequently laid down or placed over the mantle. In southeastern Australia, the proposed aniliquin impact structure has been an accidental template providing a line of least resistance for the ascent of the 2,000-kilometer diameter offshore Cape Howe plume. The western and northwestern radial arms of this plume have created the very geometry of the Lachlan Fold Belt, as well as giving rise to the spatial distribution of the granitic rocks in the belt and ultimately to the gold deposits themselves. The interplay between the templating of the mantle by meteor impacts and the ascent of plumelets, plumes, and superplumes from various discontinuities in the mantle is likely the reason that mineral deposits occur where they do. Complexity and general systems theory provide an entirely new way of seeing the Earth, and in the current context, a new way of modeling mineral deposits. Both investigate the abstract organization of phenomena independent of their substance, type, or spatial or temporal scales of existence. Western geologists generally have not considered Earth processes in terms such as far from equilibrium, dissipative processes, deterministic chaos, emergence, self-similar patterns, period doubling route to chaos, nonlinear dynamics, feedback loops, self-organization, self-organized criticality. The introduced mineral deposit model is the product of a transdisciplinary study based on these very concepts. The presented MDM is a simple one. This approach appears to be at odds with modeling complex phenomena. However, this simple approach is reconciled through two distinctions. The first is the distinction between a model and a simulation. Generally, the modelers of MDMs are creating simulations because of the vast digital databases now available and the ease of manipulating that data with inexpensive computers. However, simulations are not models. A model is inclusive, and a simulation is exclusive. Simulations are case-specific, whereas models are overviews or generalizations. A good model, in stark contrast to a good simulation, should include as little detailed information as possible. The second distinction is that mineral deposits as complex systems are emergent phenomenon. As the reader is now aware, if we disregard the agents or components in a complex system and focus entirely on the emergent phenomena, we find that it behaves in quite a simple, predictable way. The focus of the research has been on giant mineral deposits. Consensus has that the difference between a giant deposit and a small deposit is one of degree and not of kind, so the same processes that generate small deposits also form giants, but those processes are simply longer, faster, and larger. Heat, energy transfer, is the dominant factor in the genesis of giant mineral deposits. Energy transfer leaves telltale signs of its presence even when the transfer took place millions of years ago. It leaves a pattern that is interpreted to be a paleothermal map. Such a map lets us see where the vast heat has been concentrated in a large space, permitting extensive and intensive fluid flow, even allows us to deduce the duration of the process. To generate an interpreted paleothermal map, which is acceptable to the scientific community, requires that it be generated in a reproducible way. Pattern recognition algorithms provide that reproducibility. Experimentation with various approaches to pattern recognition using techniques such as wavelet transforms, morphological analyses, and cluster analyses reveal that the AutoClust algorithm gave the most consistent and most meaningful results. This algorithm reveals the radial spatial distribution of gold deposits in the Lachlan Fold Belt of southeastern Australia at two distinct scales, repeating patterns at approximately 80 kilometers and approximately 230 kilometers. Both scales of repeating patterns can be seen in the geology. The approximate 80-kilometer patterns are nested within the 230-kilometer patterns, revealing a self-similar, if not fractal, geometrical relationship. As well, it is possible to determine the maximum duration of the thermal event, that is, the proposed plumelet, which generated the patterns. In the Trunkey Creek area, for instance, the 80-kilometer pattern is present in Ordovician Silurian, that is 490 million year ago rocks, and the patterns are terminated by late Carboniferous granites, that is 300 million year ago rocks. Therefore, as a first approximation, we can assume that convection in the upper mantle beneath southeastern Australia was active for a maximum of approximately 190 million years. The radial pattern for the Trunkey Creek area is essentially intact. However, post-pattern distortion can disrupt the radial symmetry. For example, in the Gundagai area, the pattern has been dissected by northwest-southeast faulting, called the Gilmore suture, but not to the extent that the pattern has become unrecognizable. This area also shows, through the distortion of the ophiolites, the radial movement one would expect if Rayleigh-Bénard convection took place in the mantle. At the Rayleigh number appropriate for the mantle, the stable planform is a spoke pattern, where hot mantle material is moving upward near the center of the pattern and outward along the radial arms. The radial pattern in this area exhibits a characteristic that is common in southeastern Australia. There are no gold deposits at the very center of the pattern. Generally, the larger gold deposits are proximal to the center, but occur on the circumference of a circle whose center is coincident with the center of the spoke pattern. The smaller deposits occur in the radial arms. Not only do many, if not most, of the 80-kilometer diameter radial patterns have empty centers, but as well there appears to have been anti-clockwise rotation of the pattern during deposition of the gold. This is especially evident in the Bendigo-Ballarat area located in the Lachlan Fold Belt. The direction of rotation is that expected from a spinning Earth in the southern hemisphere. The Earth tide force would generate an anti-clockwise rotation. The Lachlan Fold Belt of southeastern Australia has much in common with the Great Basins centered in Nevada, U.S.A. It had been noted previously by American geologists that the giant to large sediment-hosted deposits in Nevada are spatially distributed in an area where the small epithermal deposits are scarce or absent. Most of these sediment-hosted Carlin-type deposits occur along the circumference of a northwest-southeast trending ellipse. Rolling back time and rolling back the northeast-southwest compressive forces generated by movement of the North American plate in a southwesterly direction allows a reconstruction of this ellipse to its original circular shape. This reconstruction is based in part on the circle of larger gold deposits noted for the Gundagai area in the Lachlan Fold Belt. As well, there is evidence that the gold deposits in Nevada are genetically tied to the circular Yellowstone caldera, now located 1,600 kilometers to the northeast. The deposits in the Broken Hill region of far western New South Wales show a similar ellipticity to that seen in Nevada. However, the compressional forces in eastern Australia were in and are in an east-west direction. The database for the Broken Hill region is comprehensive. This allows an analysis of the region that is not possible with lesser databases. The Broken Hill type deposits formed at higher temperatures than many of the other recognized deposit types in the region, and that temperature difference is reflected in their spatial patterning. The supergiant Broken Hill deposit occurs at the very center of a bullseye pattern that is both radial and concentric. This patterning also allows for an interpretation of the temporal relationships between the various deposit types. If the supergiant Broken Hill deposit had not been discovered over 100 years ago, it would now be possible, using the present mineral deposit model, to predict its location with an accuracy measured in tens of square kilometers. This predictive accuracy is desired by every exploration manager of every exploration company. However, this has proven not to be the case for the giant Mount Isa deposit located in northern Queensland. The Mount Isa deposit occurs along the western edge of a radial pattern with the medium-sized Mary Kathleen uranium deposit occurring at the center. The genesis of the Mount Isa deposit appears less directly related to mantle processes. It possibly occurs where it does because of far-field tectonic plate reorganization. The spatial pattern proximal to the Mount Isa deposit reveal the limitations of the presented mineral deposit model at a scale of 100 kilometers. However, at grander scales, at thousands of kilometers, the Mount Isa deposit occurs exactly where expected, on the edge of an interpreted annulus. The supergiant deposits at Broken Hill and Olympic Dam both occur on the edge of an annulus. It is proposed that the Mount Isa annulus has been dissected by mantle and crustal movement subsequent to annulus formation. The origin of the annuli is a question in its own right. There are at least two ways of creating an annulus on the Earth's surface. One is through Rayleigh-BÉNARD convection, and the other is through meteor impact. In respect to meteor impacts, it is likely that only the large meteors, that is, those greater than 10 kilometers in diameter, would have any permanent impact on the mantle. Lesser meteors would leave only a superficial scar that would be eroded away here on Earth. These lesser impact sites are obvious on planets such as the Moon and Mars that lack the dynamism of the Earth. The permanent scars in the lithospheric mantle act as accidental templates consisting of concentric and possibly radial features that impose those structures on any rocks that were subsequently laid down or placed over the mantle. In southeastern Australia, the proposed deniliquin impact structure has been an accidental template providing a line of least resistance for the ascent of the proposed 2,000-kilometer diameter offshore Cape Howe plume. The western and northwestern radial arms of this plume have created the very geometry of the Lachlan Fold Belt, as well as giving rise to the spatial distribution of the granitic rocks in the belt and ultimately to the gold deposits themselves. The northeastern and western radial arms appear to have controlled the very shape of southeastern Australian continent. Earth topography, the gravity field, geoid height, discontinuities in the mantle, Rayleigh-BÉNARD convection in the mantle, and the spatial distribution of giant mineral deposits are correlative. From the mineral deposit model point of view, the most important relationship is between the discontinuities in the mantle and Rayleigh-BÉNARD convection. The discontinuities provide the base from which convection originates. Deeper discontinuities give rise to larger diameter convection cells, that is, plumes, and the shallower discontinuities give rise to lesser diameter cells, plumelets. Rayleigh-BÉNARD convection concentrates the reservoir of heat in the mantle into specific locations in the crust. This provides the vast heat requirements for the processes that generate major hydrothermal mineral deposits. The interplay between the templating of the mantle by meteor impacts and the ascent of plumelets, plumes, or superplumes from various discontinuities in the mantle is quite possibly that very basic and perhaps quite simple concept anticipated by Associate Professor Emeritus Clifford James as to why deposits occur where they do.